You're speaking on mute.
Sorry. Uh, am I audible and can you see my screen now?
Yes.
Okay, thank you. Okay. So now we'll solve one more problem in streaming framework, and the problem is uh, estimating norm of frequency vector, right? So suppose our universe is U as per our notation, and Fi denotes frequency of say ith item in the stream. Then we want to estimate the term sigma Fi square from I1 to N, right? Right. So this is what we want to estimate. Okay. So suppose this is our, I'll just illustrate this with one example. And suppose this is our data stream. So we'll see how does this frequency vector look like. Okay. Suppose our data stream is like this. So basically, think of a vector whose size is the size of universe. Okay. So, and basically we designated one position for each element in the universe. And the corresponding position will just record the frequency of that particular item appeared in the stream, right? So for example, in this position, we'll record the frequency of A. So this is 3. A has appeared, I think, 3 times. B has appeared 3 times. C has appeared twice. D has appeared 1. E, F, G appeared 1. So our frequency vector is is 3, 3, 2, 1, 1, 1, 1. And our aim is to compute. Suppose we denote it as F. Our compute basically Fi square I from 1 to N. And this L2 norm of frequency vector, which is okay. So any doubt on the problem statement? Yes or no?
Sir, I think we are not able to see the screen. I don't know whether it's with us also the same.
No, we are able to see, sir.
Oh, okay. Maybe I'll reconnect with my laptop.
Okay. So are you able to see the screen and listen my voice?
Yes, sir.
Okay, fine. So is the problem statement clear?
Yes, sir.
Okay. So basically, given a universe, we can think of designing a vector in which we have one space dedicated for each possible element in the universe. And now, given a stream, we'll just fill the corresponding entries with the frequency of that particular item. So we can think of a vector whose size is the size of universe and which has elements at the corresponding position as the frequency of that item. And our aim is to estimate norm of that vector. Okay. So what could be the naive approach for this problem? So first we'll see naive approach, and then we'll see some elegant algorithm. Okay, so naive approach is like this, the way we have defined the problem. So basically, prepare a vector or counter of length n, size of universe, and count the corresponding so basically you can think of we have maintain an array of size n in which each element stores the count of the corresponding element, right? So what will be the space complexity of this approach?
Log n.
Sorry?
Log n bits.
Why log n? So anyway, like we are using an array of size n, so it will be anyway n, right? So this is an array of size n, where each position you are storing the counter of the corresponding element. For example, in this position we are storing the element counter for storing the frequency of A. This position we are storing the frequency of B, and so on. So we'll need to have n counter anyway. The space complexity will be anyway n. So, but in counter, what is the possible value that we can store in a counter? Right? So suppose our data stream is A1 to AM. So any counter we can store value which is as big as M, right? So to store a number which is of order M, we need log M many bits. Right? So overall complexity is order of n log m, and this is linear in n. Right? So of course this is not efficient. Okay. So basically our aim is to come up with algorithm whose space complexity is logarithmic in both and nm, whereas here it is linear in n, although it's very kind of straightforward algorithm. Okay. So aim is to come up algorithm that space logarithmic in n and m. Okay. And the algorithm that we are going to see, it's kind of classical algorithm, and this is due to Alon, Nova Alon, Matthias, Mati, yes, and Zegedi. And it's called as AMS sketch. It was discovered in 1999, and this results got Gödel Prize. it's kind of very respectable or premier result in theoretical computer science. In their paper, they considered some other problems as well. So here we'll be focusing on solving the problem of estimating L2 norm of frequency vector. But in their paper, they solve it for general LK norm, where we raise the power fi raised to power k, and still they are managed to solve the problem in logarithmic space, which is in logarithmic in both n and m. Right? But we'll see it only for L2 norm. Okay, so okay, and again our algorithm is very simple and elegant. So again, similar to count sketch, we'll use this sine function. Okay, but we'll use only one counter. Okay, what I mean will be clear in a minute. So suppose I'll just try to illustrate the algorithm with one example. So suppose we have elements in the string A, B, A, B, B, C, C, D, E, F, G, and D. So basically we'll use hash function G that basically takes a value of +1 or -1 with probability half. Right? So suppose G of A is +1, G of B is say +1, G of C is say -1, G of D is say +1, G of E is +1, E F +1, G of G is -1. So this G is for function and this G is for element. Okay, so we just store a counter where when we see corresponding element, in that counter we'll just add the corresponding G value. Okay, so for example, we see the element A. So the corresponding value is +1. So we'll add +1 over here. Okay. And now we see B. So we'll add again +1 over here. We see AA. So we'll add +1 and +1. We'll add 2B. We'll see 2B. So we'll add +1, +1. We see CC. So -1, -1. DE +1, E +1, F again +1, G -1, D +1. So whatever, basically this is some counter we are maintaining. And once our stream gets over, we'll just calculate what is the number that we have stored in that counter. So it's 5. So our estimate, we'll report our estimate as, estimator is, we'll just report the square of the number that we have stored. This Z square, which is 25. Okay, but if we just try to calculate the frequency vector, so this I use the same example. So this is the frequency vector, and if we calculate L2 norm of this frequency vector, it's turn out to be 29. Right? Okay, so any doubt on the algorithm? So you can think of this is essentially a count sketch, but there is no H function. So there is only one bucket in which everything needs to be mapped. And whatever value we get finally, we'll just take its square and report that thing as our estimate. Okay, so I'll just so any doubt on the algorithm? I'll just state the algorithm anyway. So this our algorithm is so choose a random hash function G that takes the element of the universe and map it to -1 and +1 and initialize a counter Z. And suppose if we get suppose we to say process item say J. So what we do, we just update Z with GJ, right? And we finally we report Z square estimator L2. Okay, so any doubt on the algorithm? Okay. So we'll just do the analysis. So as we have seen the count sketch algorithm, can you just help me on basically how we can write Z in terms of this hash function G? What is Z? So in count sketch, our estimator was this, where this y is corresponding to indicator random variable, and this is the value that is stored in some particular bucket, right? So the same thing we are doing it over here as well, right? So here we have only one counter, and in that counter we store basically the frequency times multiplication of this function G, right? So this thing will be Z will be J from 1 to N Fj Gj, right? And for brevity I denote this Yj. So note that in count sketch we used Yj as indicator random variable, but here we use Yj as this Gj function Gj, where and the property of this Yj is expected value of, what is the expected value of Yj?
1/k.
No. So here Yj is Gj, is a function which takes
Oh,
value +1 and -1. So expected value of Yj is 0.
got it.
Yeah, so just I'm mixing up with the notation, but I think it's kind of. And what is Yj square? it's 1. Okay, because it takes value plus 1 or minus 1. Okay. So this is Z, but our estimator is Z square, right? So which is what? So we'll just take the square of this thing, sigma Fj Tj, or maybe I should write Yj. Okay. So this is our estimator, and our aim again, we'll just try to calculate expected value and variance of this term. Okay, so its analysis is somewhat similar to count sketch. Okay, so we'll just expand this square term. So this is like sigma xi whole square is what? Sigma of xi square plus I not equal to j xi xj. This is j from 1 to n fj square yj square plus sigma I not equal to j fi fj yi yj. All right. So again, this as yj square is 1, this z square is sigma j from 1 to n. This is fj square. Fj square plus not equal to j y fj yi yj. Okay. So this is our estimator, and we'll calculate its expected value. E of z square. This is a constant, fj square. And now we have this term. So we'll apply linearity of expectation, and we get this expected value of yi and yj. So what is expected value of yi yj?
Zero.
0. Why it is 0?
We proved it last time, right?
Okay, can you recall how did we prove it? So it takes value either plus 1 or minus 1. One, it can take value by 2 ways when both yi and yj are plus 1. So that probability is 1 by 4. And when both of them are minus 1. Right? So that probability is 1 by 4. And when it can take value minus 1, when one of them is minus 1. So their corresponding probability is 1 by 4 and 1 by 4. So overall it is 0. Right? So this will be 0. And because of that, the overall this term is 0. So our expected value of z square is basically, again, it gives unbiased estimator. This is what we want to estimate. So it gives unbiased estimator of the L2 norm of frequency vector. Okay. So basically, after looking at these analysis, it may be somewhat, you may get some intuition why, like, how this hash function g is helping us to give us unbiased estimator, right? Because if you can think of this, our estimator is, this is the quantity which we want to estimate, and this is in some sense error term. And because of the way we have choose this hash function g, the expected value of that error term is turning out to be 0. All right. Okay. So now we'll calculate the variance. Okay. So it will be e of z square, which is e of z raised to power 4 minus e of z square whole square. And for brevity, I denote this sigma fj square j from 1 to n as f2. Right, or in general, denote fj raised to power k as fk, just for the brevity of notation. Okay, so this term, basically this term we have calculated. So this is e of z raised to power 4. This is f2 is equal to f2. So f2 square. So the main challenge is to compute this term, right? So we'll calculate this e of z raised to power 4. Okay, and what is z? Z is sigma fj yj. Okay, so we'll just expand this and we get, so there'll be 4 summation I from 1 to n, j from 1 to n, k from 1 to n, and l from 1 to n. fi, fj, fk, fl, yi, yj, yk, yl. Right? So I've just rewritten this thing in terms of 4 summations. Right? And after applying the linearity of expectation, we get I from I belongs to n, belongs to n, k belongs to n, fi, fj, fk, fl, expected value of yi, yj, k, and yl. Okay. So now the problem boils down to computing this expected value term. So any idea how to proceed further? Okay, so here we choose this hash function. We choose hash function G from 4-wise independent hash family, 4-wise independent universal hash family. And so basically, if it is chosen from 4-wise independent hash family, we can use this property like E of yi, yj, yk, and yl. We can just
E of
write it.
yi, E of yj.
Yes, so we can just write it like yi, E of yj, yk, and yl. If, yeah. And what is the 4-wise independence? It's like hash function, which is sampled from a hash family H, such that maybe if an element H of x1 is equal to y1 and H of x2 is equal to y2 and H of x3 equal to y3 and H of x4 equal to y4. So we call a hash function H from universe U to bucket, say size of some bucket M. Then if x1 not equal to x2 not equal to x3 not equal to x4 and y1 not equal to y2 not equal to y3 not equal to y4, then probability that h of x1 is mapped to y1 and h of x2 is mapped to y2, h of x3 is mapped to y3 and h of x4 is mapped to y4, where these xi's are from universe and these are from M. This is equal to 1 by M raised to power 4. Right. So for two universal hash functions, we only deal with x1 and x2. So probability of h of x1 is equal to y1 and h of x2 is equal to y2 is 1 by m square, where x1 not equal to x2 and y1 not equal to y2. For 4 universal hash family, we get this guarantee. Right. So this is definition of
And let's say, sir, if you have 5, so it will be 1 by m2 to the power 5.
yes.
I
So
mean,
if it is 5-wise independent hash function, this is the way we are. So this is definition of 4-wise independent hash function. Definition of independent hash function. Right. So this is the definition, and we get this. So this is the definition of hash function, 4-wise independent hash function, and we get this sort of guarantee, right? So 1 second. So hmm. So we call a hash function H that maps the element of the universe to some bucket M as 4-wise independent hash function if it satisfies the following. Right. So this is the basically the definition, and right. So in general, the same way we can define k-wise independent hash function. If we have say tuple x1 to x1 not equal to x2 not equal to x3 not equal to xk, and they are mapped to y1, y1, y2, and yk, where these yi's are different and xi's are different, then the probability that the h of x1 is equal to y1 and dot 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 h of xk is equal to yk is 1 by m raised to power k. So we call it as k-wise independent hash functions. Right. And we can construct this hash function. So the following is one example of 4-wise independent hash functions. So h is from u to m. So suppose if we sample say element a0, a1, a2, and a3 from universe, then our hash function h of say a bar x, which is a0 plus a1x plus a2x square plus a3x cube mod p mod m. And this a bar we just denote it as a0. So this is one example of 4 universal hash functions. So h of is 4-wise independent hash function. Right. So this is one example. So basically this is the definition, and this is one example of 4-wise independent hash functions. And why do we require this 4-wise independent hash functions? Because we have to analyze expectation, which involves with kind of product of uh, four random variables. Okay. So now, so basically, now the question is how to proceed forward with the analysis. Okay, so again, this yi's takes value +1 or -1. And these I, j, k, and l, so they takes value from basically 1 to n. Right. So what all term will survive in the expectation? So suppose if it is E of yi only, then its expected value is 0. But now we have 4 terms. So expected value of yi, yj, yk, and yl. So only those terms survives in which we have one index occurs 4 times. So basically, when I is equal to j is equal to k is equal to l, right? So when all this I is equal to j is equal to k is equal to l. So basically, then um, will get either +1 or -1. Sorry, we'll get +1 only. Right, so this value will be +1. And the second case is two distinct index occur twice. Basically, that is basically if I is equal to j and k is equal to L, or maybe other possible variants. So like I is equal to k and j is equal to L, and so on. Right? So any doubt on this? So how many possibilities are there in which two distinct index occur twice? So basically we have 4 index, and out of which if 2 of them are same, then basically they'll make the value yi square, right? And that value will be plus 1. And again, the remaining 2 are also same. So they'll make the value, for example, yk square, and that value will be same. And that value will be again +1, right? So there are 4 choose 2 possibilities. So 6, right? So there are 4 index, and we can choose 2 of them, and they take the same value, and remaining 2 take the same value. So there are 6 possibilities, right? So is this clear? Okay, so we'll just try to calculate this expected value of z raised to power 4. So we were here. So there are 2 cases in which the term will survive, otherwise the remaining will be 0. So for example, if in this case, when say I not equal to j k l n, then this will be equal to expected value. Basically this is, sorry, so this is, so this is equal to e of yi into e of yj, yk, and yl. And if say I not equal to j, k, l, l, so this will be 0, and therefore the overall will be 0. Right? So only those terms will survive in which either all the 4 index are same, like I equal to j equal to k equal to l, or basically they paired up. So basically I is equal to k or j equal to l, and there are 4 choose 2 possibilities. Right? So expected value of z raised to power 4 will be, when all of them are same, it will be fi raised to power 4, yi raised to power 4, and when they are paired up, then there are 6 possibilities. I is from 1 to n, and j is from I plus 1 to n, and fi square fj square. Okay, so we have this e of yi square, e of yj square. So here we have e of, and this is 1, and this is 1, and this is 1. So we left with sig. Okay. So any doubt on this? Okay. So this, for brevity, I'll write it as F4. And this term, I can write it as, this is due to simple algebra. So this is sigma fj square j from 1 to n, fj square whole square minus sigma fj raised to power 4. So this you can verify. Like, right? So this is f2 square and this is f4. Right? So finally we get 3 3f2 square minus 2f4. Right? Okay, so this is what we get. So finally our variance will be, variance of z square will be e of z raised to power 4 minus e of z square whole square. So this is 3f2 square minus twice f4 minus, this is f2 square. So overall it is twice f2 square at most. So finally our expected value of z square is f2 and variance of z square is twice of f2 square. Okay, so any doubt on the calculation that we have done so far? Okay, so again, our aim is to come up with the epsilon delta approximation. So for that, we'll use medians of mean improvement, right? So medians of okay. So let a random variable. So I'll just state what is medians of mean medians of mean concentration, and then we'll apply the same on our this AMS sketch, and we'll get epsilon delta approximation. So let random variable x be an unbiased estimator of a quantity q, that is E of x is q. Then what we do, we just repeat the experiment in which our experiment several times, and then the estimator that we come up with, we'll just try to compute uh, their statistics, and finally we come up with one final estimator. Okay, so the way we repeat it, so suppose let xij, for where I is from 1 to t and j is from 1 to k, be a collection of independent random variable where each xij is distributed identically to x, right? So okay, so suppose this is x11, x12, x1k, and basically x21, x31, and xt1. Finally, we get xtk. Okay, so this is k and this is t. So, out of these k estimator that we get, the final estimator for this row is mean of all these k estimator. Mean of k estimators. Right. So basically, for each row, we get one estimator, which is the mean of all these k estimator. And corresponding to all of these t rows, we get t estimators. And our final estimator is median of t estimators. Right. So where we choose t as order log 1 by delta and k as order of variance of x by epsilon square e of x whole square, then our new estimator suppose we denote that estimator as z, which is median of from 1 to t and mean of these rows, so which is 1 by k sigma xij j from 1 to k. Right, so essentially we are just taking the mean corresponding to the estimator we got from each of these k estimators. So we get t such estimator and we report median of those t estimators, right? Then we get the guarantee that probability that z, which is our estimator, q is the ground truth quality which we want to estimate, is more than epsilon times q is at most delta. Right, so this is called medians of mean improvement. Okay, so we'll just apply this medians of mean on this AMS sketch. Okay, so if you want to apply this medians of mean on MS sketch, what is the value of k? K is order log 1 by delta. And T is order, sorry, Okay, sorry. T is log 1 by delta. T is log 1 by delta, and K is order of variance of x by epsilon square E of x whole square. Okay, and if we put the corresponding values, like variance of our estimator is twice of f2 square, and its expected value is f2. So if we put it over here, so this will be order of twice f2 square by epsilon square into f2 square. So this is order of 1 by epsilon square, right? So if we choose this T as order log 1 by delta and K as order of 1 by epsilon square, then basically we get this epsilon delta approximation for our AMS sketch. Right. So finally, we'll just summarize with the space analysis, space complexity. Again, it consists of two parts. The first one is space required to store TK sized array. So this will be order 1 by epsilon square log 1 by delta, and each counter can store a number which is as large as m, and to store that we require log m many bits, and the second thing is space required to store hash function. So how many hash function do we require? We require t hash functions. So to store t hash functions, this will require order log 1 by delta, and each hash function will require order of log n, because essentially we need to store a number a which is from universe, is randomly sampled from the universe, and in order to store that number we require log n bits. So this will be log n, right? So overall it is again order of 1 by epsilon square log 1 by delta log m plus log n. Again the same space complexity. All right, so any doubt on whatever we have covered? Okay, so the reference for count sketch, count min sketch, and AMS sketch, I used like I referred to the excellent lecture notes by Amit Chakravarti. This is data stream algorithms. This is by and chapter 5 and chapter 6.1 and 6.2. I roughly follow their notation and analysis. So, any questions? Okay, so all right, so I'll stop here now.